So if we look at energy metabolism in normal cells, we see that the bulk of energy comes from oxidative phosphorylation with the waste products of CO2 and water. So glucose is metabolized in the glycolytic pathway to pyruvate. Pyruvate enters the mitochondria, and the Krebs cycle is fully oxidized and generates this energy through the process of oxidative phosphorylation. Very little energy is coming out of the cytoplasm in glycolysis or out of the Krebs cycle that I showed you before in normal cells. These are called substrate-level phosphorylations. They can work in the presence or absence of oxygen. You have to realize that energy is the key necessity for life. Without energy, nothing can grow. So it's very important to know where the energy comes from. Now, this is the cancer cell. Energy is coming from totally different places, the majority of energy. So the cancer cell gets very little energy from oxidative phosphorylation because the cristae and the mitochondria are abnormal, as I've just shown you. But this cell still remains alive because it generates energy in the cytoplasm with lactic acid as a waste product, which is the Warburg effect, or succinic acid as a waste product coming from the Krebs cycle. So the Krebs cycle and glycolysis generate the majority of energy through substrate-level phosphorylation, a non-oxidative process, where much less energy now comes from oxidative phosphorylation. So this is the key shift. The cancer cell is generating energy through different processes. So the question now, how does this relate to dysregulated cell growth? How does this disturbed energy metabolism link to the hallmarks of the disease? And this is what we've been able to show. We've been able to reconfigure the landscape of understanding cancer by placing the focus on the origin for this organelle, the mitochondria. So we know, and this was the concept of the oncogenic paradox that plagued and puzzled the field even to this day. You'll read and see many examples where people simply don't understand how all the provocative agents that have been linked to the origin of cancer could cause the disease through a common pathophysiological mechanism. Carcinogens cause cancer, we know that. Radiation can damage oxidative phosphorylation, leading to the origin of cancer. Intermittent hypoxia damages mitochondria, leading to the origin of cancer. Inflammation can damage mitochondrial function. Chronic inflammation is a known risk factor for the development of cancer. Rare inherited mutations like the BRCA1 and the Li-Fraumeni mutations that people recognize, they operate by damaging mitochondria. The RAS oncogene is known to be a facilitator of cancer. It damages mitochondria. Viruses, we know of many different kinds of viruses. The papillomavirus, hepatitis C virus. Viruses can cause cancer because they either the virus themselves or the products of the virus damage the mitochondria. And of course, aging. All of this mitochondrial damage leads to the reactive generation of ROS, which are reactive oxygen species. The reactive oxygen species damage the nuclear genome, lipids and proteins in the cell. So the mutations that we see in cancer come as the result of damage from reactive oxygen species. The mutations are an effect. They are not the cause of cancer. So the majority of studies on cancer have really been focusing on downstream epiphenomena, where the real origin of the disease is related to the function of the mitochondria. Now, interestingly enough, the ROS also damage oxidative phosphorylation. The mitochondria send a signal to the nucleus that the organelle is incapable of providing enough energy to maintain the life of the cell. This signaling system then turns on genes in the nucleus that upregulate substrate-level phosphorylation, like HIF1 alpha and MYC. So in order to run substrate-level phosphorylation, you need fermentable fuels, and the fermentable fuels are glucose and glutamine. So the mitochondria signals the nucleus begins to upregulate pathways, transporters to bring in glucose and glutamine through generating energy through substrate-level phosphorylation, while the mitochondria continue to suffer damage and gradually lose their ability to produce energy through OXPHOS. It is this transition from oxidative phosphorylation to substrate-level phosphorylation that ultimately leads to the development of dysregulated cell growth. So we can then link the hallmarks of cancer as defined by Hanahan and Weinberg directly back to damage to the respiration and energy transition in the cell. So the first three hallmarks, self-sufficiency, insensitivity to anti-growth, and limitless replicative potential, is the result of the cell falling back on its default state. And the default state of mammalian cells is proliferation. And proliferation was the phenotype of all cells and organisms on the planet before oxygen came into the atmosphere some 2.5 billion years ago. So the cancer cell is falling back on ancient pathways that lead to unbridled proliferation, as all cells did before oxygen came into the atmosphere. This also leads to blood vessel development in the cancer cells, which is angiogenesis in the microenvironment of the cancer cell, I should say. Also leads to evasion of apoptosis, or programmed cell death. Why is this cancer cell bypassing the natural ability to die when energy metabolism is so shifted? Because the mitochondria control apoptosis. The mitochondria act as the kill switch. If the kill switch is broken, the cell will bypass its programmed cell death mechanism, and therefore go on to proliferate.
Annotated and summarized, easy to share with loved ones. The description below the title for this video has these summary points.